How big is the universe? You might think it's infinite, but that's not what science says. It says that there's a limit to how far you can travel in space and time, and it's called the cosmic horizon. But I bet you didn't realize that there's another cosmic horizon, one that makes no sense at all. And cosmologists have been struggling with it for decades, so here it is. There's a part of the universe beyond the cosmic horizon that we should never see, but we do. Galaxies that are racing away from us faster than the speed of light. Now, that shouldn't be possible according to Einstein's theory of general relativity, which is the framework we use to describe the entire universe. General relativity says that nothing can travel faster than light, not even galaxies. But not only do we observe galaxies that are doing just that, they're accelerating away from us. So, where exactly is this paradox coming from? Let's start by talking about the cosmic horizon, the one we can actually see. The reason that we know how big the universe is, at least in terms of how far we can see, is because we can observe this cosmic microwave background radiation. It's the afterglow of the Big Bang. When the universe was very young, less than 400,000 years old, it was a hot, dense plasma. Photons would get absorbed and re-emitted constantly before they had a chance to travel very far. But as the universe expanded and cooled, those photons no longer interacted with matter. They just flew through space undisturbed, and that's when they began to reveal the structure of the early universe. This is the cosmic microwave background radiation we see today. It's a snapshot of the universe as it was 380,000 years after the Big Bang. Now, since light takes time to travel, the farther away an object is, the farther back in time we're seeing it. For distant galaxies, we're seeing light that has taken billions of years to reach us. That means the universe we're re-observing today is really a three-dimensional sphere with a radius of about 46 billion light years. Anything beyond that distance, we can't see and we can't measure. So that must be the edge of the universe, right? Well, no. General relativity tells us that space doesn't just stretch out infinitely in the way that we usually imagine it. It's more like the surface of a balloon, or really a sphere. If you stand at any point on the surface of a sphere and walk in any direction, eventually you'll get to the opposite side. That's what happens in our universe too. If you were to travel in any direction for long enough, you'd eventually come back to where you started. Space is curved in this way because of the matter that's distributed throughout the universe. All that matter warps the fabric of spacetime. And so the true size of the universe is really defined by this four-dimensional sphere, a sphere of spacetime. But if the universe is a sphere, then there is no edge. You can keep traveling indefinitely, and you'll eventually return to your starting point. But this raises another problem. We know that the universe is expanding. Distant galaxies are racing away from us. As a result, points on the cosmic microwave background are disappearing over the horizon. Every photon in that radiation has a specific wavelength, and that wavelength gets stretched as the universe expands. And once it gets stretched beyond a certain point, the photon no longer appears to be a photon. It falls out of the electromagnetic spectrum entirely and into the realm of matter particles instead. In other words, as the universe expands, photons vanish. If that's the case, then the cosmic microwave background radiation should have disappeared completely, but it hasn't. It's still there. And that poses a serious problem for physicists. It implies that new photons are being created all the time to replenish those that get lost. But we don't know of any physical process that could produce such a large number of photons. So either the physics we currently understand is incomplete or our observations are wrong. At the moment, physicists tend to favor the former. Now, these two problems together paint a pretty strange picture of the universe. On the one hand, we know that it extends infinitely beyond the cosmic horizon. We can prove that mathematically from general relativity. But on the other hand, we know that there's something preventing the cosmic microwave background radiation from disappearing, some kind of particle production that we don't understand. Those two facts together mean that there has to be new physics at play somewhere. And physicists are still searching for a complete theory that explains how everything fits together. It's important to remember that this isn't just some abstract mathematical curiosity. This is real physics with very real implications. After all, the universe we observe is only a tiny fraction of the total universe. We only see inside of this sphere, and whether or not the laws of physics change beyond that sphere could have profound consequences for humanity. If we want to go exploring out there someday, we need to know what we're getting ourselves into. At first glance, the missing physics might seem obvious. Maybe it's dark energy. The idea is that there's some kind of repulsive force causing the expansion of the universe to speed up over time. We don't know what dark energy is, but scientists have proposed many different models for how it might work. One popular model is that dark energy is a kind of quantum field that permeates all of space. Fields can have particles associated with them, and those particles have a wavelength just like photons do. So maybe those dark energy particles are what's replacing the photons that fall out of existence due to the expansion of the universe. There's just one problem with that idea. These hypothetical dark energy particles would have to be produced inside of black holes, and we've never observed that happening. So while it's possible that dark energy could be the answer, it's not very likely. Instead, most physicists think that the missing physics has to do with quantum effects near the Big Bang. According to general relativity, the Big Bang was an extremely hot, dense singularity. But physicists believe that the laws of physics as we know them break down at that point. We don't have a theory of gravity that can describe what happens inside of a black hole or at the Big Bang. It's thought that quantum effects played a crucial role in the earliest moments of the universe, and those effects may have left an imprint on the fabric of space-time itself. It is possible that the apparent creation of new photons in the cosmic microwave background is really a manifestation of that early quantum activity. The trouble is, we don't know what kind of quantum effects we might be looking for. Most physicists think that the answer lies in a yet-to-be-discovered theory known as a quantum theory of gravity. Such a theory would clarify the nature of the Big Bang and explain how the early universe evolved into the one we observe today. It would also tell us what happens inside of black holes. Unfortunately, no one has managed to construct a quantum theory of gravity yet. That said, there is some evidence that we might be on the right track. Physicists have found some unexpected correlations between the cosmic microwave background and gravitational waves, ripples in the fabric of space-time that were produced in the first moments of the universe. If these gravitational waves came from the same era as the cosmic microwave background, that would strongly suggest that they're related. In other words, the same physics that is giving rise to the missing photons might also be responsible for the gravitational waves. We're still a long way from a complete understanding, but it's not impossible that we'll solve this cosmic horizon paradox sooner rather than later. Imagine how useful that would be. Once we know what's really going on beyond the cosmic microwave background, we can use that knowledge to map the shape of the universe. And that would give us an unprecedented amount of information about the distribution of matter within the entire universe. With that map, we could learn how galaxy formation and evolution are influenced by the large-scale structure of the universe. It would be like having an all-access pass to the largest archaeological dig in history. In the meantime, though, we're left with a universe full of mysteries. We know that it extends infinitely beyond the cosmic horizon, but we also know that there's something preventing the cosmic microwave background radiation from disappearing. And until we know what that something is, we won't know how big the universe really is. Thank you for watching this video. If you would like to help support the channel, we have a platform where you can support us. Also, there's another channel that has some great videos on it that you might enjoy as well.